Okay, good morning. Um, Welcome to semester 2 of new semester, new Shaden. Uh-huh. What's that? Well, it's math, right? So any I thought you said new Shaden, not same old Shaden. Oh. It's math, right? So when you learn something, and then even when you move on to learn something different, you always end up using the things that you've learned, right? So, well, here's what we're going to learn. Here's what we're going to learn. Let's take, hey, girls. Let's say you have the curve y equals x squared. And you know that it's a parabola, right? Looks like this. Let's say that you wanted to find the area underneath that curve between 0 and 2. How would you do it? But the slope is changing all the time. Okay, I know that the bottom is 2. That is true, yes. Okay, I know that what's the height? What is it? We know it. It's 4. New Shaden, why? Because 2 squared is 4, okay? So you know that the height is 4, okay? Base times height would give us the area of this entire rectangle. Well, I mean, no, it doesn't have to do with the derivative. Doesn't have to. It's a new semester, new. You guys aren't really like thinking very much. You're just throwing out big math terms. Okay, Maddie says plus b squared equals c squared, but that would be if this were a triangle. Okay, we're close. Okay, you're right. So if we found the area of that triangle, we would be close. What is the area of that triangle? No. The area of the triangle is 4. Okay, but if we do that, whoops, we're leaving a big chunk uh, unknown. Okay, so Katie is disappointingly cheating and looking at the book. What'd you say? Yeah, right. And so what does the picture tell you? Okay, so instead of using one big triangle, which is sort of one big sort of mess, we could put a bunch of rectangles underneath here instead. We know how to find the area of rectangles, and we find the area of the individual rectangles and add them up. Then we can get a better answer for the area. Okay, how many rectangles do you want to try and use to start with? 6? Okay, well, one rectangle, Maddie, is going to be way worse than the triangle because the triangle was this much too big. The rectangle is way too big. Okay, so you want to do 2 little rectangles like this, right here and right here. Well, what would the area of this be if we did it with 2 rectangles? What is the base of this rectangle? What's the height? What's the height? Nope. 1, because like Shaden, like new Shaden did, if you take this and plug it into there, you get 1. Okay. Plus, what's the base of this rectangle? 1. What's the height of it? 4 because 2 plugged in there gives me 4. So this area is 1 plus 4, which is 5, okay, which is probably worse than the triangle that Maddie started out with in the first place. So the way that we can get closer is by using more rectangles. You want to use 4 now? Okay, so if we use 4 rectangles, then you might be able to see that there's less of the rectangles up above the curve, less extra stuff. So let's use 4 rectangles. What is the, okay, good, the base of that is 1/2. What's the height? 1/4, because if I take 1/2 and square it, I get 1/4. What's the base of the next rectangle over? 1/2 times, what's the height? 1, because if I plug this in, 1 squared is 1, plus, what's the base of this one? 1/2 again, times, how do I find the height? 1 and 1/2 squared, okay, plus, what's the base of this one? 1/2 times, what's the height? 2 squared. Boys, stop it. Stop it. What is an easier way to figure this out? You guys just like, the lack of thought is unbelievable. You're just shouting out things. What is an easier way? Think about, for like more than half a second, this math problem that I'm trying to do here. Is there an easier way that I can do it instead of going 1/2 times 1/2 squared plus 1/2 times? Okay, good. All of the bases of the rectangles are 1/2. So I can factor that out and figure out all of these things individually and then multiply it all by 1/2. Okay, and that's a little bit faster to do it that way. So this is going to be 1/4 plus 1 plus 9/4 plus 4, which is going to be 10/4 plus 5, which is, what's 10/4? 2.5. So that's going to be 1/2 of 7.5, right? Which is going to be 3.75. Okay? So, finally, closer than Maddie's opening bid of 4. Okay? Yes. How do we get the precise method? How do we get the exact answer? Right, and Payson had said that before. The way that we would get an exact answer is if we could make an infinite number of rectangles, okay? So what we're working towards when we do these is we're going to do the limit as x approaches infinity of the base of the rectangle times the height, and then that limit is going to give us the exact answer. Okay, it has nothing to do with the slope. I don't. Oh, I hope that's not the case. Did you have a question? Yeah, actually there are a couple of different ways that we can do it that we are going to talk about towards the end of the chapter. But the triangle, I'm sorry, the rectangles is the easiest, and so we're going to start with that, okay? All right, so Katie sort of cheated her way into figuring out that this is what we're trying to do by looking at this picture. So this is an example of what we were doing with many, many more rectangles than just 4. And the idea behind this is that hopefully you can see, in this case you can start with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rectangles. This extra stuff is the wasted part, right? That's the wrong part. The more rectangles you get, you should be able to see that those pieces get smaller and smaller and smaller, which is what Hero and Payson were getting at. If we were able to get an infinite number of rectangles, then there would be no waste at all, okay? If, however, we had an infinite number of rectangles, what would the base of each one of those rectangles be? How wide? Would it be infinity? Infinitesimally small, right? Because as the right 1 over infinity, because as the number of rectangles increases, the width of the rectangles actually gets smaller and smaller and smaller. Okay. Okay. So first 4 chapters were about derivatives. That's called differential calculus. Now we're going to be tackling something called integrals. Okay. Hopefully not surprisingly, this is referred to as integral calculus. Okay. Those are the 2 main parts of the class. There is, Maddie, a connection between integral calculus and differential calculus. It's called the fundamental theorem of calculus. We'll get there in this chapter later on. Okay. So I was flipping through these notes on Friday, preparing for today, preparing for the big day, and I got a little chuckle. When I first started doing these, I took the textbooks down to the copy machine and just pushed them onto the copy machine and made a PDF out of it. And so this is from my old school days, so a lot of these are going to be like, you can tell that they're just, the pages that I copied. And then I just went for it and took a razor blade and cut out the pages later on. Okay. All right. So this is all about the area problem. Like I said, it's a little introduction. We're trying to find the area underneath a curve. That's challenging. That's not something that you've ever been able to do before, because for the first time, with the exception of a circle, you have things with curved sides. Okay. And so people have messed around with this before. The way that they figured out the formula for finding the area of like, what is this, a pentagon, 1, 2, 3, 4, 5, is by just dividing it up into smaller shapes that we do know the area of. If you know how to find the area of a triangle, you can take a pentagon and divide it up into triangles, find those areas. What? It's not? I did. 1, 2, 3, 4, 5. Oh, 6. Okay. Hexagon. You can take that and divide that up into shapes that you do know the area of, figure those out, and then that would give you the area of the whole thing. Okay. But as we just talked about, it's not as easy to do that when the shape is curved, because if you try to put a shape with straight sides into a shape with curved sides, it's going to be a little bit messy. Okay. So that is the problem that we just started with. Okay. So what we're going to do, we're going to simplify this a little bit and just go from 0 to 1. And this is, Maddie is right, is a little bit like what we did when we were first learning derivatives. We're going to do this with a larger and larger and larger number of rectangles, and then we're going to figure out the limit by seeing what those numbers approach. Okay. I appreciate that you're trying to find that connection. I don't think we're quite ready to get there yet. Okay, you are ahead of everyone else as usual. Yeah, yeah. So we'll have that conversation a little bit further down the road. Okay, so how many rectangles should we go with? 5. 5. Okay. So if we do 5 rectangles, then let's see if we can do this without drawing all the rectangles. This is important. Okay, nice. So New Tegan right away says that all of the bases are going to be 0.2. Okay, how'd you get that? Okay, good. So if we take this thing right here and divide it by the number of rectangles, that will give you the base of each one. Okay. Then what are the numbers that I'm going to plug into x squared to find the heights of the rectangles? I'm going to do, it depends in a way on how we draw the rectangles, and we'll talk more about that later. But if I divide this up into 1, 2, 3, 4, 1, 2, 3, 4, 5 pieces, then the way that I get the heights of all of those rectangles is by plugging in the x value to the equation right here. Okay? Yep, exactly. So, and that is a nice easy pattern to see also. 1/5 squared plus 2/5 squared plus 3/5 squared plus 4/5 squared plus 5/5 squared. When we did that with the other one, some of those fractions reduced, but if we leave them unreduced, and I'm going to, Tegan, no offense intended, but I'm actually going to change your 0.2 into a 1/5 also, just so we're all consistent, okay? Because now this becomes really simple, right? All of the denominators are going to be 25, because 1/5 squared, and then this is going to be 1 plus 4 plus 9 plus 16 plus 25 on top, right? Okay. So then if I add those together, I get, let's see, 20, 30, 45. Is it 55? Did I do something wrong? Oh, yep, you're right. Okay, so 1/5 of 55 over 25, and that goes in there 11 times, so that's 11 over 25, which now I'm going to go back to decimal land, is 0.44. Okay? Because 5 goes in here once, 5 goes in there 11 times. Okay? All right, let's try another number of rectangles to see just the, you know, the pattern and how it works. I know I won't torture you guys too much with it, okay? Maybe. The area is not 0.4 because 0.44 because you can see from here that I have some missing some extra pieces. Okay, so let's go 10 of them. Okay, so this is going to be 1/10 using what we will call Tegan's rule. Okay, we do have to find out all of these. Yes. Yep, nice, well played. Okay, we're getting there for sure. So Elena is thinking there's got to be a better way to figure out these numbers right here. And you're absolutely right, it does involve factorials. Yeah. It's exactly like that. Yeah, right. Because we don't know yet exactly what we're doing. Okay, we're getting there though. Okay, we're getting there. Okay, so you know the bottom's going to be 100, right? And then this is going to be all of the squares, 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49 plus, what's that, 7 squared, so 8 squared is 64 plus 81, thank you, plus 100. Okay, so now we're getting into Elena's question. Isn't there a way to add up the sum of the squares without adding them all up? Yeah, is there some sort of a factorial thing that will get us out of there? Maybe. Let's see, so we knew already up to 25 is 55, right? And then, let's see, so that's 55. 36 and 64 make 100. 49 and 81 is 130. And then I got another 100 there. So 200, 330, 385. So that is going to be, if I divide 385 by 10, that's 38.5, yep, over 100, which is 0.385. Okay, any guesses? Definitely not getting closer to a whole number. What? It's not getting closer to 0.4 because we passed over that. Okay. Maybe 0.35, 0.44, 0.35. You're saying 1/3. Okay. Ooh. Okay. So not only is that a nice fraction, but you're making a geometric connection with that as well. You think it equals infinity? You think this area right here is infinite? Well, we know that's not right. Okay, well, we could jump up and we could do like, no, we're trying to find an area. We're trying to find a physical thing. It's not going to be infinity. This area is probably not going to be 1 over. Right. Right. It's not going to be 0 because, yeah, well, we had a couple of guesses there. Um, what? Maybe 1/4? Yeah. It's not particularly clear, is it? And so we would have to keep doing more and more rectangles, and this was already sort of a pain. So let's go ahead and jump ahead um, to what Elena and somebody else was getting at, that there has to be a formula for figuring this out, okay? So it turns out the answer is 1/3. Payson? No, he didn't. No, so the answer turns out to be 1/3. Let's take a look at the algebra for why that's the case, okay? Are you guys going to do this algebra? No, okay? But this is the algebra that would need to be done, all right? So the 1 over n, let's say that we took it and divided it up into n rectangles. And then what we're going to do is, like you guys said, we're going to figure out what the limit is as n approaches infinity. But let's figure out first the formula for adding up any number of rectangles. So this is Tegan's rule right here, that the base of each rectangle is going to be 1 divided by the number of rectangles that there are. And then hopefully you guys should recognize this from what we were doing before. The fractions that you end up squaring are 1 over n, 2 over n, 3 over n, 4 over n, and so forth, right? That's just like what we were doing here. We had 1 over 5, 2 over 5, 3 over 5, 4 over 5. Okay, same thing except now we are over n. So what they did is they factored out the 1 over n, and then they also factored out the 1 over n squared, which we kind of did here. This is the 1 over n squared, right? We did 5 rectangles and got 5. This is the 1 over n squared. When we did 10 rectangles, we got 1 over 100. And then that left us with this, the sum of squares. And that's where Elena said, can't we use factorials? There's got to be some formula for that. What's not factorials, it turns out to be this formula right here is how you add up any number of squares altogether. And well, no, this is only for one very specific curve. And what we're going to want to be able to do is to do this with any curve. Yes? Nope, that goes up to as many as you want, okay? So let's, why does this come out to be 6? I honestly don't know how to derive this formula from adding up all of the squares. I don't know why it's there. Hang on just a second, Elena. But we can check that this matches. When we had 5 rectangles, what did we get for this number right here? 55, just for the adding up the squares part, okay? So, I mean, you can check that, and if I plug in 5 here, it'd be 5 times 6 times 11 divided by 6. The 6's cancel, and I get 55, okay? When we had 10 rectangles, the number we got on top was 385. So if I plug 10 into here, that's 10 times 11 times 21 divided by 6. Hopefully that's 385. Okay? Okay, calculate it out while I try and answer Elena's question. Yeah. Oh. This is only for y equals x squared. Yeah. Yeah. 385. Okay. So again, I honestly don't know where this formula comes from. I would not be able to necessarily, I mean, maybe if you gave me an hour, I could sit down and try and figure that out. But this is the formula for adding up a bunch of numbers being squared, okay? So we already had the 1 over n times 1 over n squared gave us 1 over n cubed. Then we replace all of this with that crazy formula right there. And then like you guys said, we're trying to find the limit as n approaches infinity of that thing. So they did a little bit more simplifying. This n right here cancels one of those n's right there. And then I guess they just multiplied the 6 and the n together. So we've done these types of limits before. They broke it down into 1/6 times this times this. Then you can break this down into two distinct fractions. N divided by n is 1. 1 over n is 1 over n. Over here, 2n divided by n, the n's cancel and you get 2. And over here you have 1 over n. We already have had the conversation that 1 over any polynomial, as it approaches infinity, what's going to be the limit of these things? 0. So that leaves us 1/6 times 1 times 2, which works out to be 1/3. Okay? Right, yep, you're absolutely right. We could have FOILed this out on the top and figured out, we wouldn't even have to FOIL it out. If we multiply these together, that's 2n squared, yeah, you're right. And then over 6n squared, and then we could just use the highest power over highest power rule and get 1/3. Yeah, you're right. Okay? Okay, so that's a way, one way, to figure out the area in between 0 and 1 of that parabola. Okay? That's only one curve, and that's only from 0 to 1. All right? So, generally speaking, here are some things, yes. Only for that. Yeah, so that was a specific example that now we're going to refer back to as we go through and develop a general formula for doing this. Okay? All right, first thing that you should know, this is where Tegan's number comes from. This should be written down, okay? The width of all of those rectangles, which we're going to call delta x, because for those of you that had the courage to stick it out in a science class, you know that delta stands for change, okay? So the change in x, the change in the bases of those thingies, is b minus a, where in this case b is the right hand x part of the curve and a is the left hand one. So ours was simple because it was just from 0 to 1. So we knew that was always going to be 1. That's not necessarily always going to be the case. So it's b minus a divided by the number of rectangles. Okay? So that's how you find Tegan's number. Yeah? The width of each rectangular base. The delta x is the, yeah. So right here it says the width of each of the n strips. Yeah. I would call that Tegan's formula. Okay? Okay, so that's how we are going to find the bases. Okay? And then the way that we got the heights of all of the rectangles was by taking the x values and plugging them into the function that defined the curve, right? And then again, in our example, it was y equals x squared, so we just squared them. And then we wanted those, the number of rectangles to get to be larger and larger and larger. As the number of rectangles increased, the area of the rectangles got closer and closer to the curve, okay? So here it is as a formula. The area underneath a graph of a continuous function is given by the limit as n approaches infinity of the number of rectangles. And then here are the individual pieces. This is what you get for the heights. So those things are all the heights. And then these things are all of the widths, or the bases. Okay? So it's just the basic rectangle area formula, base times height, height times width, whatever. It's just that we have an infinite number of the rectangles, and all of the heights are different as they're defined by the curve. Maybe. Seems like it's important. What does what mean? So the f of x1 and f of x2 and f of x3, that's the heights of the individual rectangles, and then the delta x is the width. Okay? All right, here we go. Let's try another one. It says, let A be the area of the region that lies under the graph of f of x equals cosine of x between x equals 0 and x equals b. where b is in between 0 and 2 pi. Okay, so now we're going to do, if it's in between 0 and, if it's in between 0 and 2 pi, that's the first little, yeah, I don't know what you want to, did I, oh yeah, sorry, pi over 2. That's the first little thingy of the, right? So it says using right endpoints, find an expression for a as a limit. So according to the previous formula that we have, the area is going to equal the limit as n approaches infinity of, what are the widths of all of the little rectangles going to be? It's going to be b minus 0, or in this case just b, divided by, how many rectangles do we have? We don't know. We have n rectangles. That number is going to approach infinity. So that's going to be the widths of all of the rectangles. We're getting there. Okay, and then the way that we find the heights of all of the rectangles is we take all of the little thingies and we plug them in. So that's going to be times cosine of x0 plus cosine of x1 plus cosine of x2 plus all the way up to the very last one. Okay? I have no sympathy for you. All right, so this is me applying the formula from the previous page. The one that we were supposed to write down. This is the delta x, is the interval. That was, we went back to this thing right here. That's Tegan's thingy. So in our case it was b minus 0, or just b divided by n. And then all of the heights come from plugging the x values into this function. Payson? Why is there what? Oh, it means it just keeps going until you get to n. But since we don't know what n is, they're ellipses. Yeah, good day today. No, it's not f of x squared. It's f of x1, f of x2, f of x3, okay? F of xn. That's an n. Okay, let's do an example, and I screwed up, I'm sorry. This is supposed to start at 1, not 0. Okay, but whatever. All right, so let's estimate the area by letting b equal pi over 2, and we're going to do 4 rectangles, okay? So for this one, the area is going to be, what is this number right here? Yep, good, because we're going to do this as our base right here, divided by, how many rectangles do we have? Nope, for B they want us to do a specific number of rectangles, 4, good. So we're going to take that width, pi over 2, and divide it by 4, okay? What's that? Right here, estimate the area of pi equal to 4 subintervals, okay? All right? All right, now this is a weird one because it says take the sample points to be midpoints, okay? So I'm going to enhance. Not working. So I'm going to take this distance from 0 to pi over 2. We're going to zoom in on this a little bit. I'm going to divide that up into 4 individual pieces. What are those thingies? If I take pi over 2 and middle one's going to be pi over 4. This one's going to be pi over 8. And then this one's going to be 3 times that. 1, 2, 3 times pi over 8, so it's going to be 3 pi over 8, okay? But, this is important, it says taking the sample points to be midpoints. So the numbers that we're going to plug in are, we would draw the rectangles right from the center of those thingies instead of what we were doing with all of these other ones. The other two examples, we drew our rectangles somewhat arbitrarily, nobody commented on that, from the right-hand side, okay? So we divided this up into 5 pieces, and then we went to the right side of this and then went up to the curve and went over. What we're going to do now is we're going to go to the middle of that and then go over, okay? And you can see that in this case that would have maybe given us a better estimate because part of the rectangle would be above the curve, but part would be below, okay? So now we have to figure out what the midpoints of each one of those things is. So what is halfway in between 0 and pi over 8? Pi over 16. Okay, and then all of these other things are just sixteenths. So this is 1/16, this is 2/16, that's pi over 8. Then this one is going to be 3/16 or 3 pi over 16. 4, yep, the next one is going to be 5 pi over 16. And then this one is going to be 7 pi over 16. So these are the ones that we are going to be plugging into the cosine function to find the height of the rectangles, okay? So who's going to be my calculator person? Yes. Okay, you need to be in radians. So this is the base of all of the rectangles. The heights of the rectangles are going to be cosine of pi over 16 plus the cosine of 3 pi over 16 plus the cosine of 5 pi over 16 plus the cosine of 7 pi over 16, okay? So first of all, what is pi over 2 divided by 4? 0.39, let's go 3 decimal places, 0.3926, so 0.393, okay? What is the cosine of pi over 16? Give me 9807, so 0.981 plus 3 pi over 16. Okay, so 0.831, and you can see these values are going down because the curve is going down also. Okay, Katie, keep going. Ignore Maddie. 0.5557. Okay, so 0.556 plus, then the cosine 0.1950. Okay, so do that little simple calculation in the end. Is that what you did? You just did it all in one step, Maddie, because as usual you're 3 or 4 steps ahead of the rest of the class. Let's see if Katie gets the same answer. 0.982. Okay, well, I don't know what to tell you. You guys should get the same answer there. That's weird. You got 3 different answers by doing it 3 different ways. Okay. 1.007. Okay. So hopefully you guys can understand that what is that getting? I mean, if we did more, yeah, this is basically approximately 1. Which I don't know about you guys, but I think that's weird. Okay, that you would come up with a 1 as an answer for the area of this curved thingy that's defined by a cosine function. Doesn't, yeah, but a circle has, that makes it even weirder because a circle has pi in it, which is a never-ending or repeating decimal. So, okay, this is not circular. Or, no, the cosine curve, do you want to see that? Okay. Yeah.